so up next, we're going to talk about some current stuff, but also thinking very far forward, because everybody hates driving, right? I'd much rather have my car drive me to work than me have to drive. We want to make sure that that's nice and secure. So these guys are going to talk about whether we can trust self-driving vehicles. Let's give them a big round of applause. Have a good time.
Thank you. I'm so excited to stand here. Good afternoon. Today I bring you the latest work on attacking self-driving vehicles. The title is, Can You Trust Your Autonomous Vehicles? I would like to talk about our latest work on vehicle security. I'm Jianhao Liu from China, and I work for Qihu 360 in SkyGo team, focus research vehicle cybersecurity.
I'm Chen Yan from Zhejiang University, and Dr. Xu is my advisor. She is a professor at Zhejiang University and University of South Carolina. I believe she's hiding somewhere in the audience because she wants us to do all the work.
Okay, in this talk, we first introduce what is autonomous vehicles, the idea of car hacking by sensors, and present our attack. At last, we discuss possible defense. With the development car hacking, ranging from conventional cars with telematics to autonomous car, the car is increasing interacting with the environment. The third opens up new attack surface. In this talk, we show you our work on autonomous vehicles. So, what are autonomous vehicles? Autonomous vehicle can sense its surrounding and make driving decisions by using the machine learning algorithm. Basically, a car that can drive itself without human doing anything. According to this international standard, autonomous driving can be divided into 5 levels. An example of level 1, adaptive control, where we must put hands on the steering wheel. Level 3, conditioned automation, where hands can be off the steering wheel. Yet, the driver still needs to take over for time to time. Level 5 is full automation. A car can handle all the driving modes and drives itself without a human in it. So, basically, we can sleep in your car. Typically, Tesla is considered as level 3, and successfully, Google car will be level 5. This is the architecture of autonomous vehicles. First, the car has to have sensors to monitor these surroundings. And for more advanced cars, they will have a V2X, where V2X stands for vehicle to anything. Then, the sensor data can guide vehicle movement and to plan and control the path. The driving plans will be formed to the driver by HMI. The HMI means human-machine interface. All the driving decisions will be executed by the car. This is how automatic to driver works. Let me show a few automatic driving applications. They include autonomous lane keep, autonomous lane change, autonomous lane overtake, autonomous highway merge, and autonomous highway exit, and autonomous interchange. Autonomous vehicles have a rich set of sensors, which include the following. It's about ultrasonic sensor can identify obstacle nearby. Camera can use identical road scenes, lines, and measure car distance and speed. LiDAR creates 3D map by scanning the environment and plan the driving decision. Radar can identify cars from middle range to long range and measure the distance to car in the front. This speed is moving direction. Because these sensors, the car can sense the environment and identify what kind of obstacles are nearby. Finally, the car can make decisions for driving. Of course, the automatic driving are controlled by electronicals. Thus, to cover a regular car into self-driving car, one has added electronicals to control the ultrasonic directly. This way, the car can send commands to control the brakes, electronic power steering, and so on. So, how can I attack autonomous vehicles? Where sensor data guide to travel route of the car, and the sensor serve as the brain to control the car. Thus, we set scope of our attacks. Attacking the sensors on autonomous cars, if we can modify the sensor data in driving decision, will be made based on fact data. What is displayed on HMI may be wrong and may be mistake. The path planning may not be correct, which leads to wrong execution. In short, the reliability of the sensors will be affect the reliability of the automatic driving vehicles. Up to now, the most advanced automatic driving that we have access in Tesla. Tesla has advanced autopilot system, which relies the autonomous driving at between level 2 and level 3. Basically, Tesla has all the features of the autonomous driving. Thus, the autopilot system still requires the driver to place his hands on the steering wheel. It has already changed people's driving habits. Unluckily, this habit change has led to a recent incident, which is cause of sensor malfunction. Thus, the reliability of sensors is important. If autopilot can fail under normal yet special case, what will happen if there is intentional malicious attacks, as is same as China to have a traffic addiction. So there is 3 types of sensors in Tesla. One of millimeter wave radars. A middle range radar is mounted in front of the Tesla. And a camera. A front-looking camera is mounted on the windshield under the near rear mirror. And 12 ultrasonic sensors. Ultrasonic sensors are cloud near the front and near the bumpers. That's a video. We will show how we can fast the sensors and the cars, which make the autopilot of Tesla to a mere function. Let me show you a few videos give you the highlight of our work. The first is spoof ultrasonic to take HMI have a mere function. Now, Chen is behind the car. Chen is here. He is ready to close now. But the HMI can't display the designs.
好好，关掉。
Now, Yan Chen off the device. The HMI displayed. So,
然后再打开。
we can the HMI mistake.
然后再关掉。
Thank you. Next video is a ghost car. This is our tech go-to controller car. This is a ghost car in front, so we can start autopilot system and starting driving. But in front of the car have no car. When the car passes the Yan Chen, the ghost car can force our car to stop. It's displayed to hit the ghost car, so the car is to stop. So,
Thank you. I guess I'll take over from here. The first type of attack is on ultrasonic sensors. And we have tested this attack on Tesla, Audi, Volkswagen, and Ford. So what is an ultrasonic sensor? It is a sensor that measures distance generally within 2 meters. It is used for parking scenarios like parking assistance, parking space detection, self-parking, and also on Tesla there's a feature called summon, which means that you can park the car without even being inside the car. So in a parking scenario like this, generally there will be a display of distance. It is either acoustic or visual, so that we can know the sensor readings. So how can we misuse ultrasonic sensors? So imagine someone dislikes the owner of the shop, and he wants the car to keep backing into the glass wall. So he did something to the sensor that the car does not stop while it should. So what will happen? I believe most of you want to protect your parking spot. It is really annoying when someone gets parking into your parking spot. So instead of putting up a sign, if you can do something to the sensor that makes the car stop in the middle of parking, that would be awesome. So before going into how these misuses can be done, let me walk you through how an ultrasonic sensor works. So an ultrasonic sensor, it emits ultrasound and receive echoes based on the piezoelectric effect. I believe this technology is motivated by bats. So the sensor generates an ultrasonic pulse, and it propagates and hits an obstacle and bounces back and creates a receiver pulse. So we can measure the so if we can measure the propagation time between the transmitter pulse and the receiver pulse, and knowing the speed of sound in air, we can calculate the distance from this very simple formulation. So there are 3 types of attacks on ultrasonic sensors. The first one is jamming attack. So jamming attack generates ultrasonic noises that causes denial of service of the sensor. And spoofing attack, it crafts fake echo pulses so that it can alter distance. The third one is acoustic quieting. It means that this attack can diminish the original ultrasonic pulses so that it can hide obstacles. To validate these attacks, these are the equipment we used. So first we need ultrasonic transducers that can emit ultrasound. And second, we need signal suppliers that can generate excitation signals. In our case, we use either Arduino or a signal generator. To make it start faster and cheaper, we use off-the-shelf hardware, but you can totally design your own piece of jammer. So the basic idea of jamming attack is to inject ultrasonic noises at the resonance frequency of the sensor, which is generally between 40 to 50 kilohertz. And it can cause the denial of service of the sensor. So as illustrated in the right figure, so first there is on the sensor, there's transmitter pulse and the received echo pulse. If it generates an ultrasonic noise at the jammer, so this noise will be received by the sensor, and this noise will fully cover the original echoes. And we have tested this attack in the laboratory on 8 models of standalone sensors, and all those on 4 vehicles. So for these indoor experiments, as you can see on the right figure, it is a figure of received electrical signal at the sensor. When there's no jamming, you can see that there are acceleration pulse and the following echo pulses. So it is how it works. But when there's weak jamming signal, you can see that the noise floor has been increased. And as we increase the noise floor, you can see that when there's strong jamming, the noise can fully hide the original echoes, so no measurement is possible. So what about the sensors? What is the reading of the sensors? So basically, we get 2 very opposite types of readouts. The first one is zero distance, which means that the sensor detects something very close. And the other one is maximum distance, which means that the sensor cannot detect anything. So how should cars behave to jamming attack? Should it be zero distance or maximum distance? If it is zero distance, it means that the car detects something so that it will stop. But if it is maximum distance, it means the car cannot detect anything and the car will not stop and will keep moving. So obviously, zero distance is a fail-safe option for vehicles, right? However, according to our experiments on cars, the result is unfortunately the maximum distance. So let me show you a video that demonstrates how it is really maximum distance. So this is an ultrasonic sensor on Audi Q3. And this is a ultrasonic jammer, which is wired to a computer. And now from the screen of the car, you can see that the jammer has been detected as an obstacle, as displayed in the white bar. And we read the data from the OBD. It says distance is 28 centimeters. And now let's turn on the jammer. And the obstacle disappears. And the distance it says is maximum. So in conclusion, jamming attack can output at maximum distance, and it can hide obstacles. So let me summarize the result of jamming attack. So on ultrasonic sensors, there's zero distance and there are maximum distance for different sensors. And on cars with parking assistance, the result is maximum distance. Well, interestingly, from the menu of Tesla Model S, it says if a sensor is unable to provide feedback, this instrument panel will display an alert message. However, we have never seen this alert message. Well, another question is, how will the car behave when, like, self-parking and someone that the car actually drives itself based on these false sensor readings? So let me just show you a video of how we do this attack on Tesla Summon. So as you can see that there's nobody in the car. And this is me standing in front of the car, holding an ultrasonic jammer. And now Jianhao turned on the Tesla Summon. Well, normally the car will not move because I have been detected, right? However, when we jam the sensor, it moves and hit me. That hurts. Well, in conclusion, jamming attack can also hit obstacles when the car is driving for itself. You might ask, well, the distance is only like 20 centimeters. Can it be longer? Well, of course, because if we increase the voltage level of the jammer, like if we use ultrasonic Arduino outputs at 5 volts, if we output at 20 volts with a signal function generator, we can increase the attack distance. So in this video, there's a man standing behind the Tesla. This is not me. This is another brave man in our lab. His name is Wenyuan. This is more dangerous. So now the interferer is off, and I turn on the Tesla summon, and you can see that the car starts reversing. However, it will not move because the man has been detected. And now we turn on the function generator to turn on the interferer. So watch closely. Now we turn on the Tesla summon again. Well, it moves and hit the man and hit the interferer. So the car only stopped because the interferer has been hit. Thank you. Because the interferer has been hit and stopped working. So jamming attack, the distance can be increased if you have enough budget, right? So let me summarize the result of jamming attack on software against someone. So the car, under these scenarios, the car does not stop under strong jamming. It might hit someone or something. So there's another question. Why some sensors output their distance and some output maximum distance? Well, we believe it is because of different sensor designs. For zero distance, the sensor compares the signal with a fixed threshold. So if the signal exceeds, the voltage level exceeds a threshold, it believes that there's a justified echo. So the jamming signal actually increased the voltage level. So the sensor thinks that, hey, there's an echo right after I transmit. So it is zero. Well, for maximum distance, we kind of started the sensor on AutoQ3, broke it, probe it, and reverse the schematic. But we didn't find any useful information because it is application specific, I say. So all these signals are processed inside the chip. So to make it easier, we started another sensor, which is known as Maxona MB1200. It is another sensor that outputs maximum distance. So basically, we have to destroy the transducer on top of it and expose the circuits. So this is how it works when there's no jamming. You can see that the white line means the time of flight, and the blue line means the echoes. Well, you can see that there's excitation pulse and there are echo pulses. And if you watch closely, the time of flight exactly matched with the first echo pulse. And when there's strong jamming, when there's weak jamming, you can see that the noise floor has been increased, but the measurement is still correct. However, when there's strong jamming, you can see that the signal is totally overwhelmed by noise, and it seems that there is no echo. So the sensor outputs maximum. We believe it uses adaptive threshold, so it is used for noise suppression. Well, the designers definitely has a good intention designing this, but they didn't consider the malicious scenarios. Well, the second type of attack is spoofing attack. So the basic idea is to inject ultrasonic pulses at a certain time that can fool the sensor. So for example, if we craft a fake pulse right before the first original one, we can kind of spoof the propagation time so that we can manipulate the distance. But this attack is non-trivial because only the first justifiable echo will be processed. So there's kind of like an effective time slot, which is right after the transmitter pulse and before the first echo pulse. So you're going to have to inject within this slot to make it successful. And if we change the arriving time of the fake echo, we can manipulate the sensor readings, right? So this is a video that demonstrates the spoofing attack on Tesla. Oh, sorry. So this is jammer connected to a computer. This is a computer. And you can see that the jammer has been detected as an obstacle, and distance is 66 centimeters. And now it starts spoofing. Wow. So distance has been altered. It's a stop. And if you look outside the vehicle, there's nothing moving. And if you look at the instrument panel, the spoofing is still going on. So in conclusion, spoofing tag can alter distance. And this is a demo of spoofing tag on Audi. In this video, we just randomly alter the distance. At first, nothing is in front of the car. Well, I'm assuring you that the jumping bars are now volume indicator of the music. So spoofing tag can also alter distance on Audi. Let me summarize the result of spoofing attack. So spoofing attack can manipulate sensor readings both on standalone sensors and on cars so that we can make the car stop where it shouldn't. The third type of attack is acoustic quarantine. A method is acoustic cancellation, which means that we cancel the original one with sound of reverse phase. So, when they add up together, there's no echo at all. From our experiments, we observed that by matter of phase and amplitude adjustment, we're able to cancel ultrasound. But if you want to cancel ultrasound from the car, you're going to need to use dedicated hardware. So a easier way to do this is cloaking, which means that we absorb the ultrasound with some kind of sound-absorbing materials, like some acoustic damping foams, which is very cheap, and it has the same effect as jamming that can hide obstacles. So this is how we cloak a car. Now we drive toward the car, this lovely Panda car, and you can see that the car has been detected and displayed as the red bars on the screen. And now we'll apply the acoustic damping foam. Well, it disappears. And we drive closer to the car, still nothing. And now we remove the damping foam, and it reappears. So, so in conclusion, cloaking can hide a car. So what about human? Can cloaking also hide human? We tried this. So this is me walking across the car, and you can see that I have been detected by the sensor. But now, if I wear the damping foam, I'm invisible. And still nothing. Well, can you think of a new way to wear this foam? Here we go. This is this is the foam scar. It also works. So cloaking can hide a human. So if you want a car, a human, or glass to be invisible, just buy this. Well, by the way, behind the glass door is my advisor's office. So this is what happens when you let our students do all the work. I'm sorry. So the third type, the second type of attack is on the millimeter wave radars. So we have tested this attack on Tesla Model S because we don't have, the other 3 cars don't have a radar on it. So M&W radar, it measures distance, angle, speed, and shape, etc. from short to long distance. It is used for some high speed and critical applications like adaptive cruise control, collision avoidance, and blind spot detection. So how can we misuse radars? It is similar. So when you're driving on the highway and there's danger ahead of you, and you want to stop, but the car, if you do something to the radar, that the car does not stop where it should, it could cause some serious accidents. And if there is danger behind you and you want to steer away from it, but the radar tells you that there's something ahead of you, you have to stop. So that would be terrible. So let me walk you through how a radar works. So a radar transmits and receives electromagnetic waves and measure the propagation time and etc. It is similar to ultrasonic sensors, except that the signal is RF. So when we're dealing with RF, it is difficult to measure the time because it travels at the speed of light. So in order to do this, we have to do modulation so that we can make this process easier. So one of the most popular modulation scheme is FMCW, so which is kind of frequency modulation. And the Doppler effect can be used to measure the relative speed, and there are 2 major frequency bands, which is at 24 or 76 gigahertz. So this is how the frequency modulated continuous wave works. Basically, it is kind of like a sweeping frequency signal, so the frequency actually varies with time. And when the signal is transmitted and it hits a target and bounces back, we'll receive a similar received signal. And what we want to measure is the reflection time, but it's difficult. So we measure the difference frequency FD and calculate the time knowing the ramp slope. So sometimes when the car is moving relatively, there will be a Doppler frequency shift. So before doing the text, the first thing we have to do is to understand the radar signal. So we're going to have to analyze the signal to find out what is the frequency range, what is the modulation process, what is the ramp height, and what is the number and duration of ramp, and what is the cycle time. So after knowing this, we can know whether jamming tag or spectrum tag is feasible, right? So this is kind of like a family picture of all the equipment we use. Special thanks to Keysight Open Lab for providing us free access to this equipment, which is 3 times the price of Tesla. Well, so I'm going to explain which ones I use later. Well, I forgot one thing. It doesn't have to be so expensive because you can actually, you can just buy a radar and modify it to be your own jammer. So this is how we analyze the signal. So first we receive the radar signal with a home antenna, which is connected to a harmonic mixer, and analyze the signal from the frequency domain on the signal analyzer and on the time domain from the oscilloscope. So basically what we found is that the radar outputs at 76.65 gigahertz as a signal frequency, and bandwidth is 450 megahertz. Modulation is MCW, but we have known all the details of the radar charts, but I'm not going to tell you because I want to be responsible. So the idea of jamming tag is to jam radar within the same frequency band, which is 76 to 77 gigahertz. So we can jam at fixed frequency like this, and we can jam at sweeping frequency like this that covers all the frequency band. Well, the idea of spoofing tag is to spoof the radar with similar RF signal, something like this. Pretty straightforward. And to generate the radar signal, we have to generate the signal with a signal generator at 12 gigahertz and multiply the signal with a frequency multiplier and transmit it with a home antenna. So before showing you how the results are, let me introduce you how the autopilot displays. So the blue icons means that the traffic-aware cruise control and auto steer is on. And the blue car means the car ahead of you has been detected and locked. And we have to do the experiments when the car and equipment is stationary, because when the car is moving, and in case our attack is successful, the car might hit the equipment. And if I damage the equipment with 3 times the price of Tesla, I won't be able to graduate. So this is a demo of jamming attack. So in this video, I am standing in front of the Tesla, controlling the radio interferer, as you can see from the camera of the mobile phone. So now the autopilot is turned on, and the car containing the equipment has been detected as a blue car. And now I show how, so now the interferer is turned off. So we turn on the interferer, and you can see that the blue car disappears. And we turn off the interferer, it reappears. We have kept trying this for many, many times, and it works every time. So jamming attack on radar can hide obstacles so that the car may now stop where it should. So let me summarize the result of all the radar attacks. So for jamming attack, it can hide obstacles, which has already been detected, and either fix or spoofing frequency works. For the spoofing attack, we can spoof the distance of the car ahead. So basically, what we would have seen is that the car actually jumps forward and backward. Well, the third type of attack is on cameras. We have tested standalone cameras from Mobileye and Prompt Grid, and tested on Tesla Model S, which has a Mobileye. So camera actually detects objects by computer vision. There's forward camera and there's backward camera. It is used for lane departure warning, lane keeping, traffic sign recognition, and also for parking assistance. So how can cameras be misused? So a camera is mainly used for steering. If the camera does not work, the car may not steer where it should. So there can be some accidents. Well, the attack we have on camera is blinding attack. So basically, it means we jam there are 3 types of interferers we use. There are LED spot, laser pointer, and infrared LED spot, which are all very cheap. And there are 2 scenarios. The one is we point the interferers directly at the camera, and the other is we point the interferer at the calibration board and reflect back to the camera. So this is a result of blinding with LED. So when the LED is pointed toward the calibration board, there's only partial blinding. But when it is faced toward the camera directly, there will be total blinding. And this is a result when we use a laser beam. It is even more prominent. Either fixed laser beam or wobbling laser beam can cause total blinding. And there is something we didn't expect, is the permanent damage of the camera. So you can see that there's this black scar on the camera. And we have to send it back to the vendor and have it repaired, and it cost us a lot of money, which I don't care because it is Jianhao's camera. Well, this is a demo of blinding the camera with a laser beam. This is a view from the camera. And now we point the laser beam at the calibration board, and you can see that the effect is not very effective. However, when we point the laser beam directly at the camera, you can see that there's this blurry white and blurry red, and you cannot see anything. So you can imagine what will happen if the camera on the car has been blinded like this. So laser can blind camera. We have also tested infrared LED. It doesn't work very well. We have tested blinding cameras on Tesla. Well, the good news is the Tesla actually gave you an alert message that asks you to take over when there's jamming time. So it is kind of like a relieving response. Well, we have submitted our findings to Tesla and got their active response. They appreciate our work and they are looking into this issue. Well, looking forward, how can we improve these sensors? Well, to begin with, the sensor has to feel safe. For example, this zero or maximum distance for ultrasonic sensors, it has to be zero distance so that the car will stop instead of hitting something. And it should also be designed with anomaly detection function. I believe at least jamming attack is easier to be detected because there is a abnormal strong level of signal. And also increase the diagnosis of sensors, such as using multiple ultrasonic sensors for measuring one distance. And also using different types of sensors to, for like kind of double check. And also in the system that does the sensor data fusion, it is better if the trustworthiness of these sensors are evaluated so that when the system does not have enough confidence in the sensor data, it will stop the car from self-driving, so it can feel safe. Well, safety is always more important than convenience, right? Well, what's next? In the future, we hope to get the output out of the sensors directly. So instead of a black box approach, and we hope to read the sensor data and the actuator data. Well, we hope to carry out moving vehicle experiments to examine whether these attacks are feasible when the vehicle is moving on the road. And we hope to measure the longest, the maximum attack range and angle, and also how we can improve the performance of these attacks. Well, in conclusion, I hope what you can get from this work is that attacking existing sensors on cars is feasible. We have found many ways to fool sensors. Some attacks are easy, while some are non-trivial. So the sky is not falling. It's not like someone on the roadside can easily just attack your sensors. Well, for the manufacturers, the sensors should be designed with security in mind so that we should also always think about intentional attacks, especially when the sensors is going to play a very important role in self-driving cars. Well, for customers, do not trust semi-autonomous cars yet. You have to always be careful yourself. Well, will we have fully secure autonomous cars in the future? Let's wait and see. Well, these are the people we'd like to thank. Without the help, this work would not be possible. These are our colleagues that helped us in the experiments. If you want to know more details about this work, please check out our white paper or just write us emails. Thank you. Thank you. If you have questions, you can come up here. We'd like to answer.